Okay. So hi everyone. Before we continue, why are these? Just give me a second. Yes. Okay. So before we start the session, several things. First off, about the midterm assignment and these things. I'm planning to announce everything tonight. If I get too tired and I can't do that tonight, I will do it tomorrow. Okay. And so just a rough idea, the midterm will be after the deadline of the first assignment. So you don't need to worry about that. And I will give about, I think, I need to calculate on the calendar, but I think I will give you about 2 weeks or a bit less than more for the assignment 1. And so it means that the midterm will be around July, maybe early July. And I'll also make the announcement. So in the same announcement, I will say about the midterm, the details, when it will be, the assignment. The assignment, I will post it. I will make a date for posting it, but I think I will post it very soon. I have the questions in my mind. I just need to write them down. Okay, just give me that some time. I think the reason that a bit this lack of time has happened in my life is that this is the first semester I'm teaching these courses and I'm preparing the slides, and you know that the slides are heavy. So I'm a human, and please understand my situation. Okay, that's one thing. So I will also, in the same announcement, I will say to you for the forming teams and proposals, I think we will give maybe about a week or a week and some days for you to decide the teams and the proposals. Proposal is not graded, just 1 or 2 paragraphs of what you're gonna do in the project. And so yes, there are 3 things which I will make announcement about: assignment 1, midterm, and project proposal. And if there is not enough time for assignment 2, I will make the assignment 2 short. So it will be shorter, so you will have enough time to do the assignment 2 too. That's one thing. Another thing is that, yes.
How many people will be allowed in one group?
I need to check and I will let you know. One issue with forming teams in University of Guelph is that people can drop in the last moment. And yes, that's a big issue for forming teams. This is not allowed in other universities at this time, but this rule is here, so people can drop even at the very last moment. So it makes it hard to form teams because we don't know what is the exact number of people in the class, but at least I will assume that no one will drop, and hopefully and by the way, people might say that the slides are heavy and these things, so let me drop and these things. Decision is yours, but as this is my style, I will take it easy in this assessment, and I'll also curve the grades at the end if necessary. So yes, that's one thing. And also, my style is I try to teach in a way that I like to be taught. Okay, I always put myself in your shoes, and I said, okay, if I had a teacher, how would I want someone to teach me machine learning and deep learning? And I will teach in the same way. Okay. So this is a style that I like if I were a student. Okay, because I understand the details of the algorithms. If you don't understand the details, it means that you haven't understood the algorithm. Okay, that's one thing. And also at the same time that I try to teach well, I will try to take it easy, because I know if I don't take it easy in assessment, the course will become overwhelming. I'm completely aware of that. I was a student several years ago, so I know, I'm completely aware. I don't want to make the courses overwhelming at all. That's why you don't need to worry. And I think in the assignments, you will see that it's not very hard. I can even tell you the rough idea of the assignment questions and the midterm. for example, some data points, you will have some iterations of backpropagation or perceptron or different algorithms that we have covered. So yes, and by the way, the exam will be open books, because I don't want anyone to memorize anything. Okay, so it will be, but it will be in person. So we'll have a formal exam. Okay, that's one. And yeah, and by the last thing which I said before starting, please, the courses are also, these two courses are also gonna be offered in fall. If the department agrees, I will teach them. But my worry is that too few people have taken the courses in deep learning. So they have 50 persons capacity. In deep learning, only 7 people have taken, and in a statistical machine learning, I think 17 or 15.
People drop from this course.
No, you don't need to drop the courses that we have. I told you, I take it easy, but it doesn't mean that you shouldn't do your job. Do your best, okay? Do your best in assignments, in projects, in midterm, and I will also, if you do your best and do to your best, and then I will consider giving you a good grade, okay? But it doesn't mean that you should be lazy and don't do your test. Do your best, and I will try to be a good grader. Yes, so that's one thing. And I wanted to tell you, could you please recommend these courses to your friends, because too few people have taken the courses, and I'm worried that they even get canceled. So okay, there are 50 persons capacity per each course, and deep learning is only 7 currently, and statistical machine learning 15. Yeah, okay. Thank you very much for recommending these to your friends. Okay, so we continue. Initialization of kernel. So do you remember we were talking about, is there any question? No? Oh, okay, we were talking about what? Convolutional neural networks, right? Now we continue with, this is one of several last slides in that slide deck, initialization of kernel layer weights. Okay, you might be wondering, why am I assigning some slides for it? You just randomly initialize the weights. No, it has some mathematical rationale behind it. Let's see. Even in initialization of weights, there is something to learn. Backpropagation is gradient descent and chain rule, right? In derivatives, right? So we need to initialize the weights. Why? In gradient descent, we initialize the solution, right? And we start from that initialization. Hence, if it is not a convex optimization problem, based on different initializations, you might end up with different solutions, right? Therefore, we need to initialize that. Or weights are the optimization variables. We need to initialize them for backpropagation. Two ways of initialization. What? Learn the weights by unsupervised method, such as principal component analysis, PCA. Have you heard of that? It's rare. It's PCA is very famous, but it's rarely used to it's rare to use PCA for initialization of weights of neural network, but it is an algorithm, as some people might do. So we will see that. Another thing is initialization by random features. The most common one is this. It is related to random projection and Johnson-Lindenstrass lemma, or JL lemma. Okay, we'll see that. So method 1, learn the PCA one. Learn the weights by an unsupervised method. Okay. So this is a technique. Divide the input of the layer into patches. Okay. So it's convolutional layer, right? So divide the input of the layer into patches. You can do that. And the patch size S can be the stride of the kernel for convolution, for example, right? Shift the patches a little bit by some features or pixels. Assume you have some features, so 2D features, you have taken some patches, you are divided these to some patches, then shifted a bit to the right and to the bottom, right? Then collect all patches and reach. So what do I mean by all patches? The patches before shift and the patches after shift. Okay, and then reshape them to become column vectors. Okay. Apply principal component analysis or PCA on the patches. What does PCA do? I will teach it in statistical machine learning course soon. So what does it do? It just finds the most variant direction of data. Okay. The spread direction, yes, of the data. So do that, and then it gives you, what does it give you? An eigenvector matrix S by S. Okay. So there is a matrix of S by S whose columns are the eigenvectors of the covariance matrix. Okay. Make a matrix with the size of the input where the S by S eigenvector matrices of PCA replace the patches in this big matrix. What do I mean? What by the way, why is S by S? What is S is a small? S is the stride of the kernel. It is 2, 3, right? So when I said reshape them to become column vectors, they become, for example, what? If the if the patch size was, for example, assume it was 3, then when you reshape it, it becomes 9, 3 by 3 becomes 9. So a 9-dimensional vector, then it will be 9 by 9 covariance matrix, right? Right? Covariance matrix. It will be 9 by 9 covariance matrix. So I think it should be S squared. Sorry about that. S squared. So you will have to assume S is 3. So your patches are 3 by 3. When you reshape them, they become 9-dimensional vector. Then its covariance matrix will be 9 by 9. Therefore, you will have 9 eigenvectors. Okay. And then, so 9 eigenvectors for each patch, right? For each patch. Then replace each patch with the eigenvectors. Okay, with a matrix of eigenvectors, because this will be the matrix of eigenvectors will be 9 by 9. Each column will be an eigenvector. Okay, an eigenvector. Then replace the patches with the eigenvectors with this matrix U, and it gives you a good initialization for your weights. Okay. If you didn't understand this slide completely, see my future slide lecture on PCA in a statistical machine learning course. But even if after that, if you have a still question, let me know. Okay. But I think it's straightforward. Just think about it. What we are doing is saying that let's just find some patches and then find the eigenvectors of the covariance matrix matrices of these patches, and then replace these patches in the layer with the eigenvectors. By the way, what was the philosophy behind this shifting? We said shift them a bit. What is the philosophy behind them? Because I want to find the best eigenvectors which are robust to shift a bit, right? That's what, because that's why I'm collecting all of the patches with some shifts. So this is a good initialization, robust to some small shifts, right? Okay, and do this for all layers to find the initial kernels for every layer. Okay. Now, method 2. I think it's more interesting. Initialization by random features. Randomly do that. And this random distribution can be any distribution, Gaussian, uniform. Okay, for example, if we go to PyTorch, it gives you choices. Do you want it to be a random initialization with uniform distribution or Gaussian distribution or what? Then it is related to random projection and Johnson-Lindström's lemma, JL lemma. These are the two people who proposed this lemma. What is that? It says that set the initial values weights randomly by some stochastic distribution, such as Gaussian or uniform distribution. Okay. The values should not be too large, not to have gradient explosion, right? They also should not all be they shouldn't all be too small, not to have gradient vanishing, right? If all of the weights are very small, the gradients will vanish in backpropagation in the chain rules. If they are too big, we will have gradient explosion in the chain rules of backpropagation. So it should be some middle case scenario. Now, linear projection. So linear random projection. Rick, do you remember? I told you that every layer you can see it as a linear projection. You remember? Before activation function. Now, when the weights are random, it becomes linear random projection. Okay. So linear random projection is projection of data points onto the column space of a projection matrix where the elements of the projection matrix are random variables which are independent and identically distributed, IID. They are sampled from a distribution with zero mean and possibly scaled unit variance. Did you get it? So what do I mean? You remember U transpose X, what does it do? Yes, it projects X onto the column space of U. Recall preliminaries. If you set U, the projection matrix, to be random, where each scalar element of U is randomly sampled from some distribution with the mean zero and some unit variance. Okay, assume it is every element is sampled from a standard Gaussian distribution. Then that becomes a random projection. In other words, random projection is a function from RD to RP, which maps X to U transpose X, and U transpose X, P is the dimensionality of subspace, or the number of columns of U. Okay, so you can see it in this way or in this way. UT here is the tth column of U. So you can see U as this, which is a D by P dimensional matrix. Okay, and this is the random projection matrix. UJT, you can also write it in element wise. UJT is the jth element of U, and XJ is the jth element of X, right? So this is just projection, right? Linear projection where U is random. The elements of U are sampled from a distribution with zero mean and possibly scaled unit variance. For example, we can use the Gaussian distribution. So for each scalar element of U, we are sampling it from a standard Gaussian distribution, normal distribution. Some example distributions to use for random projection are Gaussian or Cauchy distribution, right? It is noteworthy that in some papers, the projection is normalized by this. Doesn't matter. Okay, this slide is about random projection. Okay, and I will tell you how it is related to deep learning. So if we have a data set of d-dimensional points with sample size n, we can stack the points in X. So put them column wise, it becomes a d by n dimensional matrix. Then equation 9 or 10 is stated as this. So here in equation 9, if we had 1 point, now we have n points. So X is a matrix now. Then this becomes P by n. This was P dimensional vector, but this is P by n dimensional matrix, right? We can also normalize it. Now, in contrast to other linear dimensionality reduction methods, so linear projection, you can see it as a dimensionality reduction. Why? Assume X is d-dimensional, U transpose X is p-dimensional. If P is less than D, then it is dimensionality reduction. Why? Because it reduces the dimensionality of D, okay, X. So we have various dimensionality reduction methods, which we will cover in a statistical machine learning course, such as PCA, such as FDA, and these things. Random projection is one of them, okay? So in contrast to other linear dimensionality reduction methods, which learn the projection matrix, for example, PCA learns you, FDA learns you by optimization, but random projection doesn't learn you. says randomly sample, okay? So using training data set for better data representation of class discrimination, random projection, however, does not learn the projection matrix, but randomly samples it independent of data. Okay, you might say it is stupid. Why? But interestingly, surprisingly, we'll see that random projection works. It is one of the surprising findings of machine learning in the history of machine learning. We'll see. So surprisingly, projection of data onto the column space of this random matrix works very well, although the projection matrix is completely random and independent of data. Shocking. We'll see. Although it's not as good as PCA and the learned projection matrices. I didn't claim that. I'm saying that it's good enough. Okay. And there is a theory behind that. So Johnson, Linden-Drestas, or JL lemma justifies why random projection works. For proof, see our tutorial paper, but I will have the JL lemma in the next slide. But for proof of that, see our tutorial paper. Johnson, Linden-Drestas lemma, linear and nonlinear random projections, random Fourier features, and random kitchen sinks tutorial and survey. You can find it in archive. Okay. So JL lemma is this. By the way, the proof and these things, there is no, you don't need to, it's out of the scope of this course, but feel free to see the proof if you are interested. So what is it? It was proposed in 1984. Too old. So it says for any set X, what does it mean? D-dimensional data points, but n of them. Okay. Any integer n as a sample size, which is the number of points. When I say sample size, it means the number of points. And any epsilon between 0 and 1 as error tolerance. How much do I tolerate error? Okay. Let P be a positive integer satisfying this equation 12. What is this? This is big omega notation in complexity theory. I don't know if you have passed an algorithm course or not, but if not, just a rough idea is that when you say big O notation, it is upper bound. Big omega notation is lower bound. Big theta notation is expected value, average on average, okay? So this is big omega, it means that lower bound. I think this is obvious because this is a lower bound. It is greater than or equal to this. And this is ln of natural logarithm of n, and is the number of points, over epsilon squared minus epsilon cubed. You might be wondering where this came from the proof. You can see the proof, okay? Natural logarithm, and this is the lower bound complexity. Also, some papers denote equation 12 as equation 13. Doesn't matter. They just bring the denominator to the numerator as another variable, and then they rename it. So you can take 1 over epsilon squared minus epsilon cubed as eta as 1 over eta squared, but then rename eta to epsilon again. And then you will get equation 13, okay? So by ignoring this against this in denominator, that's fine. Okay, there exists a linear map. This is what JL lemma says. A linear map from RD to RP with projection matrix this such that equation 14. So this is justifying why random projection is working. It says that what does equation 14 say? It says that this f of xi means projection, linear projection of xi by random projection, okay? So this basically means U transpose xi. This is linear projection of xj. So what is this in the middle? The distance squared Euclidean norm, or the squared distance between random projection of xi and random projection of xj. So the distance after projection. What is the right-hand side? So this is the distance before projection, right? This is also the distance before projection. And you have these terms multiplied by them. What is this saying? It's saying that the distance after projection is sandwiched between a bit between some scale of distance before projection and some other scale of distance after before projection. So basically, it means that in simple words, when you have 2 points close to each other, after random projection, they will almost fall close to each other again. You will have some error epsilon, but if you limit epsilon to 0, what happens? This sandwich is complete. It means that the distance will be preserved if epsilon is 0. But epsilon is a small usually. Surprising. Did you get it? Did you get what equation 14 is saying? It is saying that it preserves the distances of points after random projection. Okay. With what probability? So with some probability. And the probability is stated in equation 15. So the probability of this, having this equation 14, this is equation 14, right? The probability of this is 1 minus delta. Note that equation 14 is beautiful, but if it happens with low probability 10 to the minus 4, it's not useful. This is beautiful, but it needs to happen a lot with high probability. And this is the probability stated here. If delta is a small, which is a small, it means that the probability is very high. So as you see, this is a lower bound on the probability. When 1 minus delta is huge, it means that the probability is very close to 1. So with high probability, equation 14 is satisfied, and that's interesting. Okay, this is JL lemma for proof C, my tutorial. And now this explains what? What does it explain deep learning? It says that when we randomly choose the weights of the neural network initially, even before training, before the start of backpropagation, it works almost well. Okay, so it's a good initialization. That's why we are justified theoretically to initialize the weights of neural network randomly. Interesting, right? Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo. Just, I go through, these are the references. I don't explain them right now, don't have time. So this one. Okay, these are the references mentioned in the slides. Let's go to CNN nets. So far we talked about convolutional neural network and also fully connected neural network and before that. But at least I can say almost 7 years ago, and these things, it was a time for people to propose various convolutional neural networks, important ones. And I think it was an eager between people and researchers to make the neural networks as deep as they can. Okay, because it was deep learning, it was blooming. So they said, let's just do our best and make it as deep as we can. Of course, we need resources. That's why most of the important convolutional neural networks were proposed by big companies such as Google, Facebook, and these things, because they had resources. Right. Okay. So in this slide deck, we are talking about important ones, important convolutional neural network ones, some of which have novelty, some of which don't have much novelty, but they work. Okay, so it's a combination of novelty and resource. Let's see. There exist various convolutional neural networks. Some of the most important and well-known ones are listed below. AlexNet, 2010, was one of the first very successful deep neural networks. Okay, so it was published in 2017. However, it competed the ImageNet large-scale visual recognition challenge in 2010. So initially it was proposed in 2010, although it was published in 2017. Okay. Then we have VGG in 2014, reference to. Inception and GoogleNet in 2015. We have UNet in 2015. We have ResNet in 2016. And we also have DenseNet in 2017. So we'll go over each of them. Most of these neural networks were what? Were developed by big companies, and they often were winning the ImageNet large-scale visual recognition challenge, or ILSVRC in short, in different years. So this is a challenge which I will explain in the next slide. Most of them were winning networks for this challenge. This is an annual classification challenge in machine learning and image processing. So what is this? It says ImageNet, as I said, is an image. By the way, ImageNet, what is ImageNet? If you are not in machine learning, when you hear ImageNet, you might think it is a neural network. It is not. Okay, ImageNet is a data set. Okay, shouldn't confuse that with it, because many of the neural networks have net at the end, but ImageNet is a data set. ImageNet is an image data set containing 15 million labeled high resolution images with about 22,000 classes. Can you believe that? Okay, and I think one of the initial people who started collecting these, well, I think one of the, I can say, founders of this data set was Fei Li. Do you know her? Fei Li is at Stanford University. She's a professor there, working on machine learning and deep learning. Her student, Karpathy, he also helped her a lot in the research of deep learning. At the time of blooming convolutional neural networks, they were one of the big hubs for proposing various CNN methods, especially for the sake of image processing. That's why Karpathy was hired by Google, because Google at that time liked image processing by deep neural network, was looking for people, and they found that Karpathy is working very well. I think Karpathy has also a YouTube channel. You can take a look at that. But at least I know that he was working for Google. So ImageNet was initially developed by them at Stanford University. Then later, other people also helped. So the images of ImageNet were collected from the web and manually labeled, 15 million images manually labeled by humans using what? Using Amazon's mechanical turk crowdsourcing tool. So this is a tool in Amazon for labeling, okay? Since 2010, ImageNet large-scale visual recognition challenge, or ILSVRC in short, has been held. So there is a challenge since 2010. It is an annual challenge. Every year it is happening. As a part of what? As a part of the Pascal Visual Object Challenge. So ILSVRC, it has helped with deep learning and machine learning a lot, because it has motivated people to propose stronger neural networks, okay? So what is it? It is an annual classification challenge in machine learning and image processing. The dataset in ILSVRC is a subset of the ImageNet with 1,000 classes, each of which having 1,000 images. So ImageNet is very big. ILSVRC has sampled, has a subset of this dataset, big dataset, and that's 100. So it has taken only 1,000 classes, and in each class, it has taken only 1,000 images. The ILSVRC dataset has about 1.2 million high-resolution images with 1,000 classes. The images are 224 by 224 pixels with 3 channels of RGB, red, green, blue. Okay. AlexNet. The architecture of AlexNet is as follows. So what is it? So we have 8 layers. By the way, Alex, I think I have mentioned it somewhere in the slides. So Alex was something, I don't remember his family name right now, was Hinton's student. You know Hinton? Hinton is one of the biggest scholars in machine learning. Okay, he used to be a professor at the University of Toronto. So Alex was his student, and Hinton told him, okay, do this trick and do that trick, makes the neural network as deep as you can, and it will work. So Hinton gave the clue to Alex to do this. And at that time, they wanted to win that challenge that I told you. Then Alex went and worked it out. Of course, in initial trials, maybe it didn't work, so he changed some other thing in the architecture of neural network. But the idea was making the neural network as big and as deep as we can. Okay, so Hinton was his supervisor, and it worked finally. And surprisingly, it won the challenge by far, and that made the world made the bloom of neural network possible. So what does it say? And AlexNet is named after Alex, the first author of that paper. Okay, so it has 8 layers. It has 5 convolutional layers and 3 fully connected layers. Okay. So again, it's a convolutional neural network, 5 convolutional layers, 3 fully connected layers. The network of AlexNet is spread into 2 GPUs because it is too big to fit in the 3 GB memory of 1 GPU. At that time, at least, 1 GPU had 3 GB memory, maybe in their computer. And they said, okay, in order to make the network big, it doesn't fit in 1 GPU memory. So let's spread it, divide it into 2 GPUs. Okay. This also accelerates the training phase, right? When you make it parallel, it accelerates. So making neural network parallel has 2 benefits: acceleration and also memory. The settings of the layers. So layer 1 filters 224 by 224 by 3 input images. Do you remember? This is the size of images in the dataset with 96 kernels. So what is it? What do I mean by 96 kernels? The number of channels. The number of channels is 96. The number of feature maps, I mean. And then each of which is 11 by 11 by 3. And the stride is 4. We have taught all of them in the previous session, right? Okay. Layer 2 takes the output of the layer 1, which is 11 by 11 by 3, with 256, the number of feature maps, 256 kernels of size 5 by 5 by 48. It means that the output will be 5 by 5 by 48. Okay. Layer 3 then is also convolutional layer, filters 5 by 5 by 48 feature maps, outputs of layer 2, with 384 kernels of size 3 by 3 by 256. You can see the numbers are big. They're big, really. Okay. So layer 4 filters 3 by 3 by 256 feature maps, output of layer 3, with 384 again kernels of size 3 by 3 by 192. So I think I can imagine what Alex was doing. Alex first added these layers. It worked. Hinton said, go and increase 1 more layer. So Alex just increased this one. Just put yourself in the shoes of Alex. And then layer 5 filters 3 by 3 by 192 feature maps, output of layer 4, with 256 kernels of size 3 by 3 by 192. Layer 6 and 7, they are fully connected layers, right? Fully connected layers, and each of them has 4,096 neurons. Big, big. The last layer is also a fully connected layer, but with 1,000 neurons. Why? Why do we need 1,000 neurons in the last layer? Yes, exactly. Because we have 1,000 classes in the dataset. So 1 neuron per class. Why? Again, because we want to use softmax activation function. So we need the number of neurons should match the number of classes. Okay, all layers except the last layer have ReLU activation function, right? This was one of the first places that ReLU was used in deep learning. ReLU was proposed beforehand, but for what? If you have seen that reference of ReLU that I had mentioned, it was for RBM, restricted Boltzmann machine. Okay, but Hinton believed in ReLU. And he advised Alex to use ReLU activation function in his network. So it worked. This is because ReLU accelerates training and has been found to be effective, also because of the sparsity and all of things that we have talked about before. The last layer has 1000 neurons with softmax activation function, not ReLU anymore, because we want to make it like probability, right? For classification into 1000 classes. Okay. In the layer 1 and layer 2, a local response normalization is applied. So a local response normalization is applied after the ReLU activation function. What is it? So Alex said in his paper, it was empirically found to help generalization in AlexNet. Okay, they said empirically we have found it is good. Let A, X, Y, I denote the output of the kernel I at the position X, Y, followed by the ReLU activation function. Okay, so A, X, Y, I means that apply the kernel I on that output of the previous layer, and then it only consider the XY position and also pass it through the ReLU activation function. Okay. Then the local response normalization, which is used after the ReLU, is this equation. And what is this? So the summation here in the denominator is over the n adjacent kernel maps, right? Because when you say kernel I, so there are some kernels before that, some kernels after that, because we have several feature maps, right? So n adjacent kernel maps, small n, at the same time, at the same spatial position xy, and n is the total, capital N, is the total number of kernels in the layer, okay? Number of feature maps. Then, I think now we already talked about these things. So the summation, as you see, is over only the n adjacent kernels, right? This summation says only the n adjacent kernels. And this max and min is for what? Because if we are close to the boundaries, close to the end feature maps or starting feature maps, we shouldn't go to negative values or to higher values than the number of feature maps. That's why we have max and min. Okay, the hyperparameters, these are also hyperparameters. Alpha, K, where is K? K is here, K, beta is here in the power. So these were hyperparameters, and they found set them by validation set. Using validation set, recall the lecture of regularization over fitting and distance, we talked about it. So using validation set, they found the hyperparameters to be K equals 2, N equals 5, alpha equals 10 to the minus 4, and beta equals 0.75. Okay. Then after, by the way, an interesting thing, this has been extended, extinct in machine learning. Interesting. Even in big papers, sometimes you found something that at that time they thought it is good, but later they found it is useless. So they removed that. Nowadays, neural networks don't use this local response normalization. Okay, that's an interesting thing. So there is a max pooling after layer 1, layer 2, and layer 5. This is what Alex did. Okay, so max pooling. In layers 1 and 2, this pooling is applied after the local response normalization, because in layers 1 and 2, we had local response normalization. The width of pooling kernel is 3, so it's a 3 by 3. And also stride is 2. Therefore, it's using overlapping pooling, right? Because the stride is less than the width of the stride. So it has overlapping pooling. We have overlapping and non-overlapping pooling. Here, they are using overlapping pooling. As AlexNet has 60 million parameters. Can you believe that? 60 million weights. Okay. And 650,000 neurons. In the ILSVRC 2010, it achieved the top 1 and top 5 error rates with the top. What do I mean by top 1? Do you know that? It doesn't mean top 1 among other people. No. Top 1 means only consider the nearest neighbor, because you can, in embedding, you can see recall at. So you can see, for example, in k nearest neighbor, you can see whether I only consider my first nearest neighbor, top 5 means I only consider my 5 nearest neighbors, something like that. So the error rates were these: 74.5. So the accuracy was what? 100 minus 73.5, 60 something. At that time, for this hard data set, it was very wonderful. Okay. Also, top 5, the error rate is less. Of course, it's obvious. The more you consider the nearest neighbors, the easier it becomes. Okay. AlexNet was named after Alex Krzyzewski, the main co-author of the AlexNet paper. And by the way, there is a history of Alex. I think you can see it in the Wikipedia. He went to a big company, one of the companies, and then after a while, he got tired of neural network and he quit. He said, "I'm tired of the neural networks." Okay. As far as I remember, this is in my memory. I read it somewhere in Wikipedia. Okay. This is the credit of the, this is the AlexNet in the paper. So what does it say? It says that, as you see, take a look at this. We have 2 GPUs. So the above one is applied in the GPU 1, and then the below one is applied on the GPU 2, and they are replicated. So some parts of the data goes to GPU 1 and some parts goes to GPU 2. And then you in the last layer, they are concatenated, as you see, to become 1000 layers. Right? And these are, what are these? These are convolutional layers, the 5 convolutional layers, and these are the 3 fully connected layers. Right? Okay, now the loss function of AlexNet. The loss function of AlexNet is maximization of the multinomial logistic regression. Okay, do you remember logistic regression was for binary classification? So we have something named multinomial logistic regression for multi-class classification. But in simple words, it is this: if a data instance xi, if for a data instance xi, the target class label is L, okay, then it maximizes the Lth output neuron in the softmax, because it wants the probability of that class to be higher, right? So it maximizes, theta here means that the parameters of the neural network, the weights, okay? So maximize this probability of yi equals L, because I know the target label is L. So this is the softmax. What is this? The Lth output of the softmax, okay? The Lth one. Here, OJ denotes the jth output of the network. So e to the OL. OL is the Lth output of the neural network, but before the softmax. Okay, so after this, this is the softmax. OL, I feed it to the softmax, I get it e to the OL, and also this is the normalization. Summation over all of the outputs in the softmax. So, however, neural network minimizes loss function, doesn't maximize. So simply we convert this maximization to minimization by a minus behind it. Okay? Did you get it? So this is the loss function that they use. You might be wondering, why didn't they use cross entropy and these things? Because at that time it wasn't that much famous. They found out this is working, so they worked with this loss function. Okay. After AlexNet, people found out that they can make the neural networks big and deep, and they are working. Apparently, they are working. So let's defeat AlexNet and win the challenge. So VGG neural network was proposed by a team named Visual Geometry Group. So that's why its name is VGG. Visual Geometry Group is at the University of Oxford. Okay. So VGG addresses the depth of neural network. It increased the depth of the neural network to a very long depth in order to have more learnable parameters to handle the nonlinear patterns of data better. So VGG basically said, let's make the network as deep as we can. Okay. So of course, after increasing the learnable parameters, it used more training data. Otherwise, it would get overfit, right? For increasing the depth of network, it added many convolutional layers, as much as they could, okay? In other words, VGG can be considered as a convolutional neural network with too many convolutional layers. By the way, I think now I can imagine why they could do that, because they were in visual geometry group. And so they were working on graphics and these things. In graphics, they have a lot of GPUs. Okay, so they had the resource. Okay, VGG uses very small convolutional filter kernels with size 3 by 3. You might be wondering why. Can you tell me? Why did they decrease the size, the width of the kernel? So you mean that it strides more, so it can, yeah. Maybe that's one reason. Another reason that comes to my mind is that if they don't do that, it will blow up the computational resources, right? If you have too big, because the bigger kernel, it means that the more weights you have in that layer, right? Recall that we are using the same kernel for the whole layer. So if you make the kernel bigger, the more weights you have in that layer. You already made the depth very deep. It's already very deep. If in each layer you have a lot of weights, it will blow up the computational resource. So that's one reason. Another reason, you will have more weights, you will overfit it more easily because you don't have enough data, right? They didn't have the whole infinite number of data. So they had to somewhere, so they said, okay, let's increase the depth, but we should sacrifice the kernel size, something like that. Okay, there is a trade-off. Okay, network architecture of VGG, what is it? So the means of RGB images were subtracted from the images as a pre-processing in VGG. So this makes the mean of data 0. Now I think you can see the roots of all of the techniques used nowadays in deep learning. If you go to industry and these things, one of the pre-processing things that you might do in neural network is remove the mean, subtract the mean. These ideas came from the big papers like these, VGG and these things, okay? Most of the kernels were of size 3 by 3. A few ones, however, were also of size 1 by 1. What does it do? Can you believe that? You might be thinking that it is ridiculous to have kernel sizes of 1 by 1, because kernel multiplies elements and then divides by, but it's 1 by 1. It means that we have a linear transformation. So they wanted to add some linear transformation too, okay? Because kernels, you can see it as nonlinear. If it has width more than 1, then it becomes nonlinear, okay? Convolution. However, when it is 1 by 1, it becomes linear transformation. The stride of the convolution is set to 1 because why? Because when it was 3 by 3, they already reduced the width of the kernel. So they said, we shouldn't jump. Let's at least, although we made the kernel small, let's at least go slowly, 1 by 1 pixel at a time, right? Do you see the justification and the line of thought of them? Okay. For the 3 by 3 convolutions, also the pattern size was 1. Max pooling, they use max pooling because Alex used that and it worked. Okay. Max pooling is used with width 2 and a stride 2. So it is a non-overlapping pooling. Okay. Alex used overlapping. They said, let's make a change. They made it non-overlapping. In various versions, so they have versions of VGG. In various versions of VGG, the number of convolutional layers differ, but this number is usually big. This number is usually big. After the convolutional layers, after them, there are 3 fully connected layers inspired by AlexNet. The first 2 fully connected layers have 4,096 neurons, and the last layer has again 1,000 layers. They copied this part, I think, from AlexNet for classification into 1,000 classes. Okay, all hidden layers have ReLU activation function. What do I mean by hidden layer? The layers except the last layer. And the last layer has softmax, similar to AlexNet. All versions of VGG except one of them do not use local response normalization, which was used in AlexNet. So they found out that it's not required because it doesn't improve the performance much. And after VGG, also all of the papers and people in machine learning, they also didn't use local response normalization following VGG. Okay. So they use mini batch stochastic gradient descent with momentum for training VGG. And the batch size was 256, a big number, a big number. Also, you should note that these are the techniques you should learn, okay? Note that the batch size is usually set to a number which is a power of 2. These techniques are good for people, especially in industry, okay? So set it, these parts that I'm telling you are not theoretical. These parts are for experience, okay? So usually set the batch size to a power of 2. Okay, that's one thing. The momentum parameter was set to 0.9. Why? It's a big number. So momentum parameter is between 0 and 1. When it's closer to 1, it means that the more I notice my previous update, so the less oscillation I have. Okay, they didn't want to have a lot of oscillation in training, so they increased the momentum parameter. So they had high momentum in VGG. We will see in one of the following neural networks, they were inspired by VGG and they set the momentum to be high. Okay. This is set to a number close to 1, not to have much oscillation in training. Weight decay, they used weight decay. Recall regularization in deep learning neural network, we talked about it. Weight decay with L2 norm was used for regularization. Why did they do that? Not to have overfitting. Why? They are very deep. They are very prone to overfitting. They have to use regularization not to overfit. Okay. The regularization parameter of weight decay was set to 5 times 10 to the minus 4, which is a small. Why? There is always a y for everything. Why? Because if it is big, we will not notice the actual non-regularized loss function. The actual loss function is important. It shouldn't be much impacted by the regularization term. So the regularization parameter is small. Okay. The initial learning rate was 10 to the minus 2, a small number. And it was decreased by a factor of 10, divided by 10 every time the validation accuracy stopped improving. Interesting. They combined the idea of decreasing or adaptive learning rate, such as used in Adam and these things, and the idea of early stopping. So the idea of early stopping was what? To stop. Exactly. When we don't have, the validation error goes up while the training error is going down, the pattern, I mean. Then we stop the training. They got the idea, but they didn't stop the training. They said, let's train further. However, we decreased it. Whenever this happens, we decrease the learning rate, okay? And the initial learning rate also should be small enough. Why? Again, not to have too much oscillation. Not to have oscillation. Also, it shouldn't be too small. Why? So we have progress in training. Let us put ourselves in their shoes, the people of VGG lab. I think initially, when they trained the neural network, they faced oscillation in the training. Okay, then they said how to resolve this issue. They came up with 2 solutions. One of them is decreasing the learning rate whenever validation error goes up. Okay. Also, the second one, high momentum. So with these techniques, they were resolving their issues. And you can see an example of VGG network architecture. So it's deep and it has a lot of convolutional layers. Now Inception and GoogleNet. Inception is a module of neural network proposed in 3, okay? Reference 3. So it's a module. Inception, okay? The same paper which proposed Inception, paper 3, it proposed GoogleNet also. What is GoogleNet? It is composed of Inception modules. So when you stack some Inception modules, it becomes GoogleNet. Why did they name it GoogleNet? For 2 reasons. Because first off, they were Google employees, so they wanted it to be named after Google. Another reason is that, interestingly, they played around with the name GoogleNet. So you can make the L of Google capital, and at the end, it becomes like LeNet. LeNet was one of the initial convolutional neural networks proposed by LeCun et al. You remember? So they just wanted to make it fun. Okay. So in ILSVRC 2014, GoogleNet achieved the top result and won the competition in 2014. There were 2 ways to increase the number of learnable parameters in a neural network. What are the 2 ways? Exactly. What? Exactly. Depth. One of them is depth, increasing the depth, and one of them is number of hidden neurons. You can increase them, or both, right? So this increase in the number of learnable parameters has 2 drawbacks. 2 drawbacks, exactly. First, it makes the network prone to overfitting, especially if there are not sufficient label training data. And you know that label training data is expensive. Why? Because we need humans to label them. Second, more parameters need more training, requiring more computational resource. So if you you need 1 week to train, for example, 20 layers. If you make it 50 layers, then you might need several months, okay, to train them. For resolving these 2 drawbacks, the Inception module was introduced, which, what does it say? It inserts sparsity to the network. This is also beneficial for the Bettina sparsity principle and Occam's razor. We see it a lot in machine learning, okay? So it is possible to suppose that this justification is a justification of Inception paper, GoogleNet paper. What do they say? It is possible to suppose that every neuron in the previous layer of a layer corresponds to some region of the input image, okay? So you can assume that when you have some neurons in the layer, every neuron corresponds to some pixels, some regions in the input image, okay? On the one hand, in the initial layers of network, the correlated neurons concentrate in a single neuron, okay? So when we have correlated neurons, they concentrate on a single region, because of course, for the same region, similar neurons should be fired, okay? As a result, many clusters of neurons concentrate in a single region. Then these clusters for a single region can be covered by a layer of 1-by-1 convolution. 1-by-1 convolution does a linear transformation. So they said some regions are covered by some neurons. Let me capture them by 1-by-1 convolution. Okay. Note that a 1-by-1 convolution is a linear transformation. Okay. On the other hand, there are a smaller number of more spatially spread clusters of neurons. What do I mean? So consider regions of the input. Usually, the neurons fired by the same region are closer to each other. Okay, so we have a small clusters usually. So they are 1-by-1 convolution is enough to capture them. However, some of them are spread. So we need larger convolutions. Therefore, they used also 3-by-3 and 5-by-5. However, they didn't go further. Why? Because it becomes more rare to have neurons fired with the same region, but they are very sparse from each other. They are very spread from each other. I think I need to restate it. So it is very rare to happen to have for this to happen, that we have a single region, but corresponding neurons, but its corresponding neurons which are fired together fall far away from each other in the layer. Okay. Therefore, we don't need further bigger convolutions. 1 by 1, 3 by 3, and 5 by 5 are enough. Another thing which is important. Yeah, I think, yeah, that's good. So moreover, because of the benefits of the pooling, do you remember? We talked about pooling in the previous session. They also use 3 by 3 max pooling, because pooling also, for example, is makes it a bit robust to translation a bit. Do you remember? We talked about these things. So in summary, they are using 1 by 1 convolution, 3 by 3 convolution, 5 by 5 convolution, and 3 by 3 max pooling. This is the previous layer. It goes to all of these, and then they are concatenated and they go to the next layer. This is an inception module. Okay. And also, you should note that only small convolutional kernels are used, 1 by 1, 3 by 3, by 5 by 5. This explains why the inception module is sparse, as it does not use large convolutional kernels, which are denser. Okay, the bigger the kernel, the denser it is. Recall that lecture that we talked about convolution, the previous lecture. GoogLeNet stacks the inception modules as its layers. Okay. The number of 1 by 1, 3 by 3, and 5 by 5 convolutional layers can change in the inception module depending on where it is used in the network. So we have a stack of inception modules, but some of them are closer to the input, some of them are closer to the output, right? Some of them are in the middle. Depending on where the inception module is, the number of 1 by 1, 3 by 3, and 5 by 5 convolutions change. Note that this is not just one by one convolution. It says 1 by 1 convolutions, 3 by 3 convolutions, 5 by 5 convolutions, and 3 by 3 max pooling. So these are several 1 by 1, several 3 by 3, several 5 by 5. The number depends on where it is in the GoogLeNet. Okay. Now, which one is which? So in the initial layers, we usually have very fine-tuned features. So they, if you train the neural network, you'll see very detailed features are extracted in the initial layers. Very abstract and vague features are trained in the last layers. Therefore, it inspires us to use more 1 by 1 convolutions, or more smaller convolutions in the input layers, and more bigger convolutions in the last layers. Okay, so that's one thing. Okay, having larger convolutional kernels results in too much computational complexity. So people in Google worked it out and they found out it's not working. So this was their idea. They did it. They coded that. It's not working. Why? They get the memory error. Okay. So they said, okay, it has too much computational complexity even in Google, because, for example, the 5 by 5 convolution is applied on the result of the 5 by 5 convolution in the previous layer. Having multiple layers of these large convolutions results in computational blow up, even in Google servers. So what do? To resolve this problem, they did dimensionality reduction by 1 by 1 convolution. Okay. So you can see it as a linear projection. So they did convolutional dimensionality reduction. They added that. So they changed, they modified. They had a meeting, they modified the inception module. How? They added these 1 by 1 convolutions, and also at the output of max pooling, they had 1 by 1 convolutions. So what does it do? If you add this, it ignores that in the previous layer you also had 3 by 3 or 5 by 5. It becomes kind of reset, okay, at every layer. So because of this, then they resolve this issue. So finally, they use this inception module. This is the GoogLeNet. You see that? This is input. Am I right? Yes. And this is output. You can see it's too big even to fit in a one page. So these are, what are these? Inception modules, right? Okay. Network architecture. The means of they also inspired by VGG. They subtracted the mean as pre-processing. GoogleNet is a stack of inception modules as its layers. All the convolutions, including the ones within the inception modules, use ReLU activation function. I think after AlexNet, people almost use ReLU everywhere. UNet is the next one. What is it? UNet was proposed in reference for biomedical image processing application, which was biomedical image segmentation. So UNet was for biomedical application. Interesting. It was a winning submission for the EASB challenge for segmentation of neural structures in the electron microscopic stacks. Do we have people here from biomedical area? No? I have worked in that area. There are some important conferences in that area. One of them is MICAI, okay? One of them is EASB. EASB is for, I think, IEEE. MICAI is for is published in a Springer. So these are, so EASB is one of the important ones, and it had a challenge for image segmentation. What do we mean by image segmentation? Consider a histopathology image, okay? Then what happens? You will have tumorous regions, and you also have normal regions. So you need to segment it. Or you have cells. You want to find where is the nucleus and where is the non-nucleus parts. So image segmentation is important for image processing in my biomedical applications. UNet was proposed for that. So it is named UNet. Why? Because its shape is like the letter U. Okay. A UNet has a contracting path, so like the downward edge of U, I mean this. Then a symmetric expanding path like the upward edge of U, I mean this. Okay. So this is contracting part, this is expansive part, expanding part. The contracting path is for capturing the context, and the expanding path is for precise localization. Okay. So what is it saying? The network architecture of UNet. The contracting path. So it has the layers have 3 by 3 convolutions followed by a ReLU activation functions. Now, can you see that in this bigger one? So here, these are 3 by 3 convolutions and ReLU activation function. You see also these. So and after every 2 layers, we have some downsampling. This is downsampling. This is downsampling. Downsampling. How can we do downsampling? Recall previous lecture. One of the benefits of pooling is downsampling. So we can use pooling, max pooling 2 by 2 for downsampling. Okay. And sorry. So after every 2 3 by 3 convolutions followed by ReLU activation functions, max pooling of width 2 and stride 2 is used for downsampling. At every downsampling, the number of feature channels is also doubled. They double it, the number of feature channels. Why? Because they want to make it like U. Initially, it's like this, then it becomes a bit width. And empirically, they found that it is working well, okay? So the expansive path now, the layers have 3 by 3 convolutions followed by ReLU activation functions again. So these are also 3 by 3 followed by ReLU, these. And then after every 2 ones, they have the upsample, So as you see, it's kind of symmetric. Wherever we had downsampling, now we have upsampling. How do we do upsampling? This is a technique, again, in deep learning. We'll see that. How? Using, it's called up convolution, also called transpose convolution. You can see it as reverse of convolution, okay? So because what does convolution do? You multiply a window onto something, and then you replace that with 1 pixel. In upsampling, you have 1 pixel, you make it 1 window, okay? So the other way around. For upsampling, we'll see an example of it. And at every upsampling, the number of feature channels is halved, because in every downsampling, we were doubling the number of feature channels. After every upsampling, the result of upsampling is concatenated with the cropped output of the corresponding layer in the contractive path. What do I mean? I mean this. So these are, it means that take a copy and crop it and then concatenate with this upsampling. So these two are concatenated to form this. Okay. So in the middle of U, we have some copies also. So why do they need cropping? So they copy and crop, because in the border pixels are removed at every convolution. In simple words, they coded that without cropping. They faced error. They found out, they thought about it, why this is happening. They found out that the borders are removed for convolutions and these things, and then they found out, okay, they have to crop, and then it worked. Okay. It's obvious that these are the errors of their code that they resolved. Okay. An example of the transpose convolution credit of this image is this website. So you can see it in this. So consider this is the kernel, this is the input. Okay. This is the input. We want to upsample it to become this output. So 2 by 2 becomes 3 by 3. How do we do? So this is the kernel. Multiply this with the elements of this, with all of the elements, and multiply this with this and put it here. Okay. Then multiply, multiply this with this and then put it here. Multiply this with this this one, put it here, and also for this, put it here. So all of them become 3. Then then consider this one, the top right one, 1. Multiply this to each of the elements of this kernel and put them here. So 1 times 0 becomes 0, 1 times 1 becomes 1, 1 times 2 becomes 2, 1 times 3 becomes 3. Then consider this. Do this for all of the elements of input. So here 2 times 3, 0, 0, 2 times 1, 2, etc. Also for 3, 3 times 0, 0, 3 times 1, 3, and this. And then add all of them together. So when I say add, these are zeros now. The other elements are zeros. Then you will end up with this, okay? This is called transpose convolution or up convolution. The regular convolution was down convolution, okay? And UNet was primarily implemented in Caffe library for deep learning. What is Caffe? So nowadays we have PyTorch, TensorFlow, Keras. One of the famous ones at that time, which is extinct now, is Caffe. Okay. So they coded that with Caffe. Because of the large input tiles of biomedical images, because they're very big, they're very large, the batch size was set to 1 in UNet. Only 1 image at a time, at every batch. Okay. Similar to VGG, when batch size is 1, what does it mean, by the way? It means it's a stochastic gradient descent. It's not mini batch stochastic gradient descent anymore. Similar to VGG, UNet also sets the momentum parameter to 0.9. So see, they also wanted high momentum. They didn't want to have oscillation. The final feature map of UNet has the same size as the input image. I think it's obvious because it's symmetric, right? We started with the image, we should end up with the size of image again. The final feature map has C number of channels. Okay, what do I mean? By the way, what is the intention? Why did they want the output to have the same size as the input? Can you tell me? Exactly, because it's image segmentation. Because I want to classify the pixels of the image into the classes, right? So the output should be similar to the input in terms of size. And for each output feature corresponding to each pixel, they have C number of channels. Why? Because we have C classes, okay? And with softmax activation function. So for every pixel, we can see which class it belongs to, the prediction of the network. C the number of classes in the image segmentation. The last function of unit is cross entropy for classification of pixels into one of the classes of segmentation, right? ResNet. Let me finish this slide deck and then we'll have break. ResNet. ResNet is one of the ones which is actually, in addition to resource, it is actually very novel, okay? So its idea is novel. It has been empirically observed that in very deep neural networks, for example, with more than 20 layers, by increasing the depth of network, accuracy saturates and then degrades rapidly. Can you believe that? What do I mean? What do I mean? People at that time said, let's increase the depth as much as we want. They increased the depth. They saw, surprisingly, for example, with 20 layers, the error would go to 10 to the minus 4 at the end. But when they increase the depth, it will saturate and it stagnates at 10 to the minus 3, for example. The training error goes up. It was very surprising for them. Do you know why? Because assume you have 20 layers, it learns something, okay? If you were human, if the network was a human, you add some layers to it, it becomes 30 layers. If the network could think, it would say, okay, if 20 layers is good enough for me, let me learn the 20 layers, and the additional layers, I will learn them to be identity map. So it shouldn't get worse. You are giving it more resource, it can make them identity map. However, it got worse. Okay, that was surprising. They called this degradation problem. Okay. Then, in order to resolve that issue, they proposed ResNet, residual network. ResNet, short for residual network, was proposed, which uses deep residual learning. The idea is called deep residual learning for resolving the degradation problem. Okay, in the regular networks, it is hoped that each few stacked layers directly fit a desired underlying mapping. Okay, so we have some underlying mapping, you want to find that. What do I mean underlying map? You can see every classification and regression both as a regression problem. So you're fitting something, okay? You have some underlying mapping and you want to directly fit something to that. However, in the deep residual learning, each few stacked layers fit a residual mapping rather than the direct underlying mapping, okay? So what do I mean by that? Let the desired original underlying mapping be denoted by h of x, where x is the input, right? And then in deep residual learning, the stacked nonlinear layers fit another mapping rather than fitting h of x. They fit h of x minus x. Okay, I'll call it f of x. This is definition. I define it to be f of x. Restate this equation 3, it becomes equation 4. So h of x equals f of x plus x. Okay. Then write it in the network architecture format. So you have x. This is f of x. Then this means that add output of f of x with the input x. So bring this, make a copy, add it to the output of f of x. It gives you f of x plus x. This is the module used in ResNet. Okay? And the justification and the proof is this, just equations 3 and 4. Okay? So, as you see, they are adding, but this adding, if you restate it, it becomes residual. That's why it's called ResNet. Okay? Benefit of ResNet. In backpropagation, gradient can flow directly through the identity function from the next layers to the previous layers. Did you get it? So in backpropagation, we have backpropagative gradients, right? In regular network, what happens? The gradient would go through this. But in ResNet, the gradient would go through this and this. Therefore, we'll face gradient vanishing less, gradient explosion less, because we have a direct flow. It's like you are going in a highway and there is some other way too that you bypass the traffic. Okay, something like that. The deep residual learning postulates that it is easier to optimize the residual mapping than to optimize the desired original underlying mapping. I think it's obvious because we have a bypassable gradient flow, which is empirically also this postulation was approved to be correct. Okay. Variance of ResNet. We have ResNet 18. So the more the number, it means that the deeper it is, the more parameters it has. ResNet 18 with 18 layers. ResNet 34, ResNet 50, ResNet 101. So in regular computers, not even in laptops, in regular PC computers, we worked it out. Sometimes even for ResNet 34, we faced memory error. So now that's why people use ResNet 18 a lot. Okay, it's very famous. One of the most famous convolutional neural networks nowadays is ResNet. People use that a lot. Okay. Then choose based on your computer, memory, CPU, application data. Maybe your data requires a lot of layers and parameters, depending on your application. Comparison of architectures of regular net, VGG, and ResNet. So you can see this. This is VGG. This is regular network with a lot of layers. But this is ResNet, where you have these. You have these bypasses. Okay. Each of these is a residual block. Interesting. DenseNet. Okay, ResNet said what? Let me have a bypass. Oh, we will have break. Just give me a second. ResNet says we have a bypass, right? Of one layer. DenseNet says, why don't we do it for all layers and connect every layer to all other layers? Did you get it? So ResNet says, let me connect me to the output of me only. DenseNet says, connect you to the output of you and then to the next output also. And then to the third output. Do it for all of the layers. So DenseNet was inspired by ResNet. Okay. So empirically, it was observed that convolutional neural networks can become deeper, more accurate, and efficient to train if there exists shorter connections between the initial layers and the last layers. Okay, I think it's obvious because of gradient flow, bypass of gradient flow. So we don't have vanishing gradients and explosion of gradients. In dense convolutional network, or DenseNet in short, every layer is connected to every other layer in forward way. Okay. In a regular network with L layers, the number of weight matrices is L, as every layer is connected to its only next subsequent layer, right? However, in DenseNet, we have L times L plus 1 over 2 weight matrices between the layers, as every layer is connected to all its next layers and not merely to its next subsequent layer. So first layer is connected to the second layer, to the third layer, to the fourth layer. Second layer is connected to the third layer, fourth layer, fifth layer, etc. Okay. In other words, all layers are connected to each other. Okay. And why do we call it DenseNet? Because it's very dense. You have a lot of layers between each other, weights between each other. Benefits of DenseNet. Alleviate means makes it less. Alleviate the gradient vanishing problem. I think it's obvious. You have a bypass of gradient. Because in backpropagation, gradient can flow directly through all layers to every other previous layers. And then strengthen the feature propagation. You can propagate the features to each other, right? Encourage feature reuse. Reuse the features, right? From layers to layers. Reduce the number of learnable parameters. This might be surprising to you. You are increasing the number of weights. Why is it decreasing? Why is it saying that I'm reducing the number of learnable parameters? This is because they are adding a lot of layers, weights between the layers, so they don't need to make it very deep. So they're allowed to decrease the depth by adding the additional weights between the layers to have the same performance as very deep networks. Deep networks such as VGG, they had to become deep with big data in order to handle nonlinearity of data. But DenseNet says, I don't need to become that much deep because I already have a lot of weights in the middle. Okay, that's the reason. Let FLX denote the composite function of batch normalization, convolution, ReLU activation function, and possibly pooling at the layer L. What do I mean by composite function? Take all of them together. So it's a function. Batch normalization is a function. Convolution is a function. So take batch normalization, then do convolution, then do ReLU, then do pooling. It becomes FLX at the layer L. ResNet does this. So the output of FLX, where this is the output of the previous layer, you you feed it to FL. The output of that will be added to the previous input. It gives me XL, right? However, DenseNet is this equation 6. So it concatenates all of the outputs of all of the previous layers, and then it feeds them to FL, to this layer, right? In other words, it uses direct connections from each layer to all subsequent layers. DenseNet is composed of several dense blocks. If you think that DenseNet is just this, you are wrong. This is just a part of DenseNet, okay? So DenseNet has some dense blocks, and each dense block is what I told you. So it has several dense blocks, where in each dense block, every layer is connected to all its subsequent layers. So like this, dense block 1, dense block 2, dense block 3, right? In the middle of them, we have transition layers between the dense blocks, which perform convolution followed by pooling. So convolution, pooling, convolution, pooling, okay? In the dense blocks, the composite function FLX specifically consists of batch normalization, 3x3 convolution, ReLU activation function. So in the dense blocks, we don't have pooling, but we have pooling in the transition layers. You might be wondering why. Why? Why do we have dense blocks, and why don't we consider the whole DenseNet to be one dense block with too many layers? Because it will blow up computationally. If you make one very big dense block, it will blow up computationally. So let's make it modular, okay? That's the reason. In this way, you will be allowed to have more number of layers without computational blow up. Then, okay, every transition layer consists of batch normalization, 1x1 convolution, average pooling with a width 2. The last transition layer, however, is an average pooling followed by a linear layer. Why? Because we want to do classification with softmax activation function, whose number of neurons is the number of classes, right? In the dense block, every convolution has some number of channels. Okay, do you agree? We have some feature maps. This number of channels is named growth rate in the paper of DenseNet. They named it growth rate. Now they also discussed this. The Elf layer in a dense block has K0 plus K times L minus 1 input feature maps, where K0 is the number of channels in the input data. What do I mean? If it is RGB, K0 is 3. Okay, and K is a growth rate in all previous layers inside the block. They assumed that the feature maps of the layers is the same, and they named it K. Okay. L minus 1 means that all of the previous layers. So the number of channels which are concatenated to each other in every dense block is K0 plus K times L minus 1. It is empirically observed that a small growth rate, K equals 12, is sufficient for DenseNet. To me, 12 is big, but at that time, apparently they had a lot of resources. They said, okay, 12 is good enough. Okay. So these are the references that were mentioned in this slide. Okay, let's come back at 5 to 9. Thank you. Okay, everyone, shall we start? Guys, let's start. Thank you. So now we move to recurrent neural networks and long short-term memory networks. These are for sequence modeling, okay? So useful for any sequence, such as we have various sequence data, such as speech recognition, such as speech recognition, text processing, natural language processing, such as gene expression, such as stock prediction. These are all sequences, right? Two most well-known ones are speech recognition and text processing. So before the era of transformers, nowadays is the era of transformers in deep learning, regular neural networks could not process sequences such as sentences, which is sentences are sequences of words, right? Or speech, sequences of phonemes, properly without any recurrence. Okay. But at that time, we needed recurrence in order to do that. And today we are going to talk about it. So recurrent neural network, or RNN in short, what does it do? It was proposed in reference 1. It is a dynamical system which considers recurrence. We will talk about it. In recurrence, the output of a model is fed as the input to the model again in the next time step. Okay, as it is a sequence thing, we can feed the output to as the input for the next step. One of the main training algorithms for RNN is backpropagation through time. So we already saw backpropagation. Today we'll see backpropagation through time, or BPTT in short. Okay, developed by several works. These references, which is similar to the backpropagation algorithm, but has also chain rule through time. Okay, not only it has chain rule in the regular backpropagation, it has also chain rule through time. Okay, we'll see. There were some problems with gradient vanishing or explosion for long-term dependencies in RNN. We'll see that. Then several solutions were proposed for this issue, some of which are close to identity weight matrix, long delays, leaky units, and echo state networks. We will talk about them. Okay. This is just an introduction. Sequence modeling requires both short-term and long-term dependencies. Do you know why? I give you 2 examples for you to understand what I mean. For short-term dependencies that we need, consider this sentence, which is a sequence of words. The police is chasing the thief. The police is chasing the thief. In this sequence, the words police and thief are related to each other. They are opposite, you can see. They're related to each other, with short-term dependency, because how many words are in between police and thief? Is cheating the 3. So they are very close to each other in the sequence. Another example for the long-term dependency. I was born in France. My father was working there for many years during my childhood. My family had a great time there while my father was making money in his business there. That is why I know how to speak French. Okay. In humans' mind, we understand that this French is related to this France at the start of the paragraph, right? But there are too many words between them. Therefore, we need long dependency as well. Okay, long-term dependency. So both short-term and long-term dependencies are required. That inspired researchers to propose long short-term memory or LSTM networks, okay, to handle both short-term and long-term dependencies. Later, gated recurrent unit, or GRU in short, was proposed, reference 17, which simplified LSTM to reduce its unnecessary complexity. Okay, so GRU came in order to simplify LSTM. RNN and LSTM networks are causal models, right? What do I mean by causal models? They condition every sequence element on the previous elements in the sequence. So in other words, they process the sequence in one direction, okay? For example, in English, left to right, right? Later, researchers showed that processing the sequence in both directions can perform better for the sequences which can be processed offline. Why? Because in order to, for example, in English, in order to also handle or process the sequence from right to left, you already need to know the future words too, right? Otherwise, you don't know what is the starting word in the other direction. So, however, this is not an unrealistic assumption. Why? Even in the live situations, we can assume they are offline. How? If the chunks of sequence can be saved and processed. For example, we are talking to a computer, and we have a speech recognition program on the computer. The computer can wait for me to complete a sentence and then process it, right? That's one way. So we can wait for chunks of data. Or in text, we already usually have the text. We usually have the text already to process. So we can do it in an offline way. Therefore, bidirectional RNN and bidirectional LSTM were proposed to process sequences in both directions. Okay. Then the embeddings from language model, or ELMO, was proposed, which is a language model, okay, for natural language processing. And it makes use of bidirectional LSTM. ELMO is also famous. It was famous before proposal of transformers, okay? So whatever I talked about, we'll go into their details now. Recurrent neural network. So just give me a sec. Yes. Recurrent neural network. A dynamical system is recursive, and its classical form is as follows. This is a dynamical system. This is not just for deep learning and machine learning. This is also used in chaos theory and physics and these things. So it's also used in mathematics, physics, and these things. Where T, by the way, for people who are in mechanical engineering, I think they must have seen that a lot. Okay, where T denotes the time step. Okay, HT is the state at time T, and F theta is a function fixed between the states of all time steps. Why? Because the previous state is fed as the input to F theta to give me the next state. Okay, and as you see, there is a recursion here. Dynamical systems are widely used in chaos theory. We can have a dynamical system with external input signal where xt denotes the input signal at time t. Okay, so we can have additional input xt in addition to this equation 1. So what does it mean? So this is equation 1. What do I mean by this? This is just a notation. It means that if you unfold it, it becomes like this. Okay, so f theta gives me ht minus 1. If you feed it to f theta again, gives me ht. Feed it to f theta again, gives me ht plus 1, etc. And this one dot on it is here. What does it mean? It means the only one time step before that. So only one time step. For example, if we had two dots, two dots here, what did it mean? It means that we would be like this. Every output is connected to two next things. If I had 3, what would it mean? Did you understand what I'm talking about? Okay, I think it's obvious. So this is only 1. And we can also have input x. So if you unfold it, it means this. For ht minus 1, I require both f theta and xt minus 1. And for then I feed ht minus 1 and xt minus 1 to f theta to give me ht. Then I feed both ht and xt to f theta to give me ht plus 1, etc. And so on. Okay? Did you get it? Okay. The state ht can be considered. Why do I call it h, by the way? Because you can see it as hidden states. Okay? Hidden state. H stands for hidden here. Can be considered as a summary of the past sequence of inputs and states, right? It has a summary of information from previous states. I think it rings something in your mind if you have seen Markovian property in these things. We will see. So Markovian property, what did Markov say? Have you heard of hidden Markov models in machine learning? Or Markov models? It's just saying that when you have some states connecting to each other, similar to a dynamical system, then Markov said it becomes very complicated. Okay, let me assume that so for example, assume I have ht, it depends on ht minus 1, ht minus 2 until h0, right? The more t goes up, the more conditions I have. Markov, who was a scientist, said, let's simplify or relax the model in order for every state to depend on its previous state. Okay? In this way, it is simplified. But why is it justified? Why can we relax this to become this? Of course, we'll have some loss of information, but there is some justification behind it. It's because ht minus 1 is also conditioned on ht minus 2. ht minus 2 is also conditioned on ht minus 3. So the information of ht minus 3 is kind of encapsulated in ht minus 2. The information of ht minus 2 is encapsulated to ht minus 1, and ht depends on ht1 minus 1. So in other words, implicitly, ht is a condition on all of them. Although we have some loss of information by this relaxation, okay? If we say relax this to become this only one level before, it's then Markov property with one level. If we say ht depends on ht minus 1 and ht minus 2, it's Markov property with 2 levels. So we have levels of Markovian property, okay? Markov property, Markovian property. Markov models or hidden Markov models, which I will cover in the statistical machine learning course, I think, they have this assumption. They say, okay, let me assume that I only depend on my previous state. Okay, so it's very closely related. Recurrent neural networks are closely related to Markov models. That was just in parentheses. So it has a summary of past sequences of inputs and states. If a different function f theta is defined for each possible sequence length, the model will not have generalization. Why? Consider this. this dynamical system, equation 2, or the figure. We are always using f theta between them. And f theta is the same thing, right? Can we change that? So depending on t, I also change f theta. We can do that, but it makes the model very complex. Hence, it makes it overfitted. Okay, we don't want to have that. Therefore, we fix f theta for the sake of generalization. If the same parameters are used for any sequence length, the model will have generalization properties. Therefore, parameters are shared for all lengths and between all states. Okay, so we are using the same f theta. Such a dynamical system with parameter sharing can be implemented as a neural network with weights, right? And such a neural network is called recurrent neural network, or RNN. It was first proposed in 1986. In RNN, the same weight matrices are used for all time slides. So the same f theta. You can see RNN here in this figure. So you can see W here as f theta, the same weight matrices. It doesn't depend on t between them. Also, so here, take a look at that. HT. So I define some IT. IT is p-dimensional, okay, vector at time t. Here I have the state from the previous step, ht minus 1. I have W playing the role of f theta. I also have the input xt, but I will also multiply it with some weights u. So you have ux plus w times the previous state. I feed it plus some bias. I also consider the bias for the sake of intercept. Okay, so it gives me some IT. What is it? The input of the state. Here, it is here, input of the state. Then I pass it through some activation function, hyperbolic tangent. Okay, hyperbolic tangent, which is between -1 and 1. And that's why it's a p-dimensional vector whose elements are between -1 and 1. And you can see it as this. Okay, so I'm just replacing So I'm replacing IT here inside. And YT, the output, is q-dimensional. And you can see it as V times the output of HT, that's the state HT, plus some bias again, BY, for the sake of intercept. So I have two biases, BI and BY. Okay. If there is an activation function at the end, so we already had an activation function for HT. I'm not talking about that. We might have also activation function at the end, at the output of neural network. So why you can see it as the output of neural network, right? So the input here, this is input. These are outputs. These are states, right? But you might have activation function for the output, such as softmax. Why? For the sake of classification. Okay, you want to, for example, use cross entropy at the output layer. Then we denote it with y hat t, which is this activation function of yt. If it is softmax, it is this. Okay, and q is the number of output neurons. ytj denotes the jth component of yt in this equation. Okay. Any questions? So, no. Okay, now that we know what recurrent neural network is, its architecture. Now let's train it. Let's train it. How? Using backpropagation through time. We'll see that. By the way, the derivatives of them I will explain to you, but just try to understand them. There is no need for any memorization on anything. Just try to understand them. So one of the methods for training RNN is backpropagation through time, or BPTT, which is very similar to backpropagation algorithm because it is based on gradient descent and chain rule, but it also has chain rule through time. BPT was developed by several works. This algorithm is solid, is very solid in theory. However, it does not show the best performance in practice. That's why RNN is not used much nowadays. They are using LSTM and these things. LSTM is also not used much. So backpropagation through time works, but not very well. In BPTT, the loss is considered as a summation of loss functions at the previous time steps until now. So what do I mean? So at every time step, you have some loss value. But from starting the training until now, from the starting the sequence until now, t equals 0, t equals 1, t equals 2, until now, you have some loss values at some them. However, there is a problem. The more we progress, the more the summation blows up. Therefore, we need to have some window. We need to have some window of the previous steps, okay? So let the window be t of size t, capital T. Therefore, I have summation from t equals 1 to t. But here in the notation, for the sake of simplicity, I assume t equals 1 means my current time. T equals 2, my previous time. T equals 3, my 2 previous times. Did you get it? So I'm looking at time backwards. Okay. So what does this mean that we have a window? Basically means that it is a T order Markov property. T level with T levels. Markov property that I talked to you about. Only consider the T previous states. Okay. Therefore, the loss function is this. L1 is a loss function at the current time slot. Okay. This loss functions, this loss function needs to be optimized using gradient descent and chain rule. Okay. Therefore, we calculate for gradient descent. What do? We take derivative with respect to optimization variable, and it gives us the gradient, and we use it in the gradient descent update, right? So let's do that. What are the optimization variables? What are them? All of them. All of these YT, HT, V, W, U, BI, BY. Let's do them one by one. Okay. Do you remember? According to this, I'm talking about. According to these 3 equations, these are all of the optimization variables. Let's do that. We had this. This is loss L, right? Which is a scalar. If there is no activation function at the last layer, the gradient of the loss function of RNN with respect to the output at time t, what does it mean? The whole of this sentence is just this. That's why mathematics is very beautiful, because you can write the whole sentence as one small thing. Okay, derivative of L with respect to YT. What is it? By chain rule, you can write a derivative of L with respect to LT times derivative of LT with respect to YT. Right? Why don't I have summation? Because YT only depends on LT, only depends on YT. For YT, you don't need LT minus 1. Right? That's why I don't have summation in the chain rule here. Okay. Derivative of L with respect to LT according to this equation, what is it? Guys, can you help me here? I want you to also participate in the derivatives. Derivative of L with respect to LT is what? 1. Exactly, it's 1. Why? Because it's with respect to LT for a specific T. Okay, so all of the other LTs are constant. And we only LT. So it's on 1, and you will end up only with this. Derivative of LT with respect to YT. The gradient of the loss function at time t with respect to the output of time, derivative of LT with respect to YT. What is it? Let's calculate this now. It's calculated based on the formula of the loss function. Do you agree? LT, what is LT? Some loss function, such as cross entropy, whatever. YT is the output of neural network. So you can simply use the derivative of loss function. Loss function has some formula. Take the derivative. Okay. However, what if I have activation function at the output layer? That's a pain in the neck. We need to do the chain rule again. So derivative of LT with respect to IT, I write it derivative of L with respect to LT times derivative of LT with respect to Y hat T, which is output of activation, derivative of Y hat T with respect to YT. This is one. So this is the derivative of activation function. Whatever activation function you use, it has some derivative. And derivative of LT with respect to Y hat T, again, that's the derivative of last function. Right? Okay, I'm repeating these just for us to be convenient. So the gradient of the last function now with respect to HT. So we calculated one of the gradients already, finished. With respect to output is done. Now with respect to state, HT. What is it? I can write it as, so HT, again, I need to do chain rule, but change in HT affects both YT and HT plus 1. So I have HT here, it affects YT. It also, so here, according to this, it also affects the next state. So HT change in HT affects YT and HT plus 1. Therefore, I need to have this summation for the chain rules. Derivative of L with respect to YT times derivative of YT with respect to HT plus derivative of L with respect to HT plus 1 times derivative of HT plus 1 with respect to HT. Okay? Now, we know that according to this equation, this was equation 5. Okay? What is the derivative of YT with respect to HT? According to this equation, it's just V. Do you agree? It's V. Okay. Now I name derivative of L with respect to HT, which is this, by delta T. I name it. Similar naming we had in backpropagation. I name it delta T. So this is here. Okay. Now what happens? We had this, I'm repeating them here. Also, according to equations 3 and 4, so here, this was 3, equation 3. This was equation 4. This is for IT, HT. Let me write it for IT plus 1 and HT plus 1. Okay? So this T minus 1 becomes T. This T becomes T plus 1, etc. I think you understand what I'm talking about. Okay? Therefore, derivative of HT plus 1. Why do I need this, by the way? Why do I need this? Because here, I have this term. I want to calculate this. Okay? Derivative of HT plus 1 with respect to HT, what is it? What is it? It's derivative of, I can, according to chain rule, I can write it as derivative of IT here, HT IT plus 1 with respect to HT, because IT plus 1 is dependent on HT. Transpose, why do I need this transpose? In chain rule of vectors, I need transpose, okay? Because these are not scalars. These are matrices and vectors, okay? And derivative of HT, by the way, you don't need to worry. I don't ask this in the exam, okay? You don't need to worry. Listen without any worry. So with derivative of HT plus 1 with respect to IT plus 1. So this is chain rule. So what is it then? Derivative of IT plus 1 with respect to HT according to this equation 12 is W. Okay. Derivative of HT plus 1 with respect to IT plus 1 is here. Okay. What was according to this equation 13? This is tangent hyperbolic. The relation is tangent hyperbolic, hyperbolic tangent. This is the formula for derivative of hyperbolic tangent. Okay. For vectors and matrices. And this is identity matrix. Okay. So I replace this derivative with this. Okay, it's done. We found this term. We found this term. We found this term. Now, this is also delta T plus 1. If I calculate delta T, so it's already done. Now I think we only need delta derivative of L with respect to YT. but we already calculated that in this slide. Do you see that? In equation 8, we already calculated that. So I'm repeating equations 5 and 8 that we found. Okay. And we also had this. This is our definition that we had. Okay. So for all of the times we already found them, but for time slot t equals capital T, what do I mean? Very end of the window. Okay. The derivative of L with respect to h capital T is much simpler. Why? Because delta T, you can write it as derivative of L with respect to h capital T by chain rule. I write it as the derivative of L with respect to yt capital T times derivative of y capital T with respect to h capital T. Okay. According to this equation, this derivative of yt with respect to ht is v, and this derivative of L with respect to yt, according to equation 8, which is this, is equal to derivative of lt with respect to yt. And this derivative is computed based on the formula of the loss function. Okay. I'm going very fast on these because I just want you to understand a rough idea of these. But for more, if you want to get deep in them, just replay the video several times and listen to me, and I think you will get what I'm talking about. Okay. The gradient of the loss function of RNN with respect to now weight matrix V. So the next gradient, what is it? Derivative of L with respect to V, it's a Q by P dimensional. Why? Because V is Q by P dimensional. Okay. I can write it as derivative of L with respect to yt times derivative of yt with respect to V, but I need to sum over the window. Why? Because V exists in all of the time slots, not just this time slot. Okay. So I need to have the summation in the chain rule. Okay. Change in V affects the loss in all of the time slots in the window. Okay. Then, because of equations 8 and 5, which were these, derivative of yt with respect to V, what is it? According to this equation, it's ht, but as it is vectors, it's ht transpose. Okay. The derivative, now this derivative, what about this? This is just the derivative of loss function, right? So we calculated the gradient with respect to V also. Gradient with respect to W, with respect to them. So it's a P by P dimensional. Why? Because W is P by P dimensional, and L is a scalar loss function. Okay. A good technique, listen to me, a good technique in derivatives. For more information, see my tutorial on optimization. In the preliminary section, I have talked about Magnus Noether convention. Just Control F and search for Magnus in that paper and you will find it. Okay. There is a technique says that, do you remember I said derivative of, in the preliminaries, I said derivative of matrix with respect to matrix becomes a tensor, or derivative of vector with respect to matrix also becomes a tensor. In order to handle that and make it only matrix, we vectorize them. So here we are using that technique. Okay, vectorize and then devectorize it. So here, derivative of ht with respect to w transpose. So I'm writing derivative of L with respect to w. I'm writing it as chain rule. Derivative of L with respect to ht times derivative of ht with respect to w. But as it is columns and vectors, I have transpose, and also the order is changed. So first derivative of ht with respect to w, then that derivative of L with respect to ht. Doesn't matter. Okay, this is chain rule in matrix format. Okay, and this for this is a pain in the neck. Why? Because it's derivative of vector with respect to matrix. It becomes a tensor. So I have to use the Magnus convention in order to make it like a easy vectorize it. So I write this as derivative of ht with respect to it times derivative of it with respect to w. Okay, again, another chain rule here. So derivative of ht with respect to it, how do I calculate it? Recall the relation of ht and it, what was hyperbolic tangent. Here it is. Where was that? Hyperbolic tangent. So this derivative is simply the derivative of hyperbolic tangent. Derivative of it with respect to w is this. And this is the Kronecker product used in Magnus-Noether convention. For more information, see the tutorial. These slides of derivatives are just for interested students. You can bypass them if you don't want. But this is interesting for you to learn the techniques, okay? Gradient with respect to u. Gradient with respect to u. If you understand how these derivatives are working, you will become it will be very easy for you to calculate gradients for matrices and vectors. So it's a good practice for you. So gradient of the loss function with respect to u, what is it? It's a p by d dimensional matrix. Why? Because u is p by d dimensional. Then what happens? Again, I need to use Magnus-Noether convention. How? So by chain rule, I have derivative of derivative of L with respect to ht times derivative of ht with respect to u. I need summation. Why? Because u exists for all of the time slots. Okay. This devectorization is for the Magnus-Noether convention. Then this derivative, the derivative of L with respect to ht, we already computed that in the previous slides. Okay. In equation 17. And derivative of ht with respect to u in equation 17 is this. So this derivative, I'm talking about this derivative. What is this? It's derivative of, I can write it as by chain rule, as derivative of ht with respect to it times derivative of it with respect to u. Derivative of it with respect to u by Magnus convention is this, where this is Kronecker product. Okay. Don't be scared by the word Kronecker product. It's very easy. You know what Kronecker product is? Kronecker product. Wikipedia. I mean by Kronecker product, I mean this. Do you see the? So here, if I have A Kronecker product B between two matrices, this becomes A11 times the whole B, A12 times the whole B. So each element of A is multiplied by all of the matrix B. And so if A is, for example, 3 by 4, B is 5 by 6, the whole thing becomes 3 times 5, 15 by 24. Do you get it? The number of rows is multiplication of number of rows in A and B. Number of columns is the multiplication of number of columns in A and B. Okay, this is Kronecker product. We also have Kronecker delta. So two Kronecker terminologies are used in machine learning and mathematics. Kronecker product is this. Kronecker delta, we already talked about that in our courses. So for example, in Kronecker, what was Kronecker product? What was Kronecker delta? Do you remember? I said delta ij. If I equals j, it is 1. If I is not equal to j, it's 0. So you shouldn't confuse these two things. This is Kronecker delta. That was Kronecker product. Okay. Kronecker delta is used a lot in machine learning, also in physics. Einstein used that a lot. Kronecker delta. Okay. So especially relativity. So we already talked about this slide. Let's go to the next slide. Gradient with respect to BI, the bias. What is that? Derivative of L with respect to BI I can write it as chain rule. Derivative of L with respect to HT times derivative of HT with respect to BI, chain rule. But I need summation because BI exists in all of the time slots. Derivative of L with respect to HT already calculated before. Derivative of HT with respect to BI is new. So again, by chain rule, it can be written as derivative of HT with respect to IT times derivative of IT with respect to BI. Okay. What is derivative of IT with respect to BI? It's 1. Do you remember? Let's go back to the formula of IT. Where was that? It's here. IT equals WHT minus 1 plus UXT plus BI. So derivative of IT with respect to BI is 1. Therefore, I can write it as this. Okay. Now, gradient with respect to BY. So we had these. I'm repeating them. The gradient of the last function with respect to bias BY is this. But again, chain rule. Derivative of L with respect to YT times derivative of YT with respect to, because YT is here, with respect to BY, but I need summation as BY exists in all time slots. Then, according to this equation, derivative of YT with respect to BY is 1. So it becomes simplified as this. Derivative of LT with respect to YT is just the derivative of last function. Do you see that? Simple. Now that we calculated all of the gradients, it's time to use them in gradient descent. So we calculated all of these gradients. All of them with learning rate eta. Let's update them. For HT, I need to do it for all of the window, right? This is backpropagation through time. Nothing complicated in my opinion. Okay. The derivatives, by the way, you can either calculate them manually by hand or by computer or numerically. Do you know, by the way, this is good to talk about. Do you know how they do it numerically, numerical derivative in the deep learning? Sorry about that. Let's talk about this because I think this is important. Assume I wanna assume I have a vector A, B, C, D. My device has some issues. Sorry about that. Okay. This is numerical derivative in deep learning uses A, B, C, D, then E, F. Name it as, I don't know. I say eta 1, eta 2. Derivative of eta 1 with respect to eta 2. How do you do that? Numerically. What A, B, C, D, and E, F, these are some values, okay? So some variables. Then derivative of eta 1 with eta 2, it becomes a matrix first off. Why? Because it's derivative of a vector with respect to another vector, right? And so, for example, this is 4 by 1, this is 2 by 1. Therefore, this becomes what? 4 by 2, right? You can see it as 2 by 4, but if you see it as 2 by 4, you need to transpose everything in your calculations. Okay, doesn't matter. 4 by 2. So it means like this, 4 by 2. Okay, 4 by 2. Now we have how many? 8 things to fill out in the computer. So how do we do that? For this one, this is corresponds to A, B, C, D. This corresponds to E and F. Okay. Then for this one, for example, what do? I tweak E a bit. What do I mean? I have E plus epsilon and F. Okay. I tweak E a bit. I don't change any other thing. F is fixed. Okay. So first off, once I have E and F, I feed it to the network or whatever. It gives me some eta 1, so some values. Okay. Let me call it A1, B1, C1, D1. Okay. Then I tweak E a bit. Then they change. A1, B1, C1, D1 change. I denote them by A2, B2, C2, D2. Okay. Did you get it? Then I just see how much change because this is corresponding to A, row A. So I change A1 and A2. How much change did I have from A1 to A2? Okay. Then I use the formula of derivative. What was the formula of derivative? I can't memorize any formula. Just T. Limit of f of A plus h minus f of A over h. What does it mean? In our formulation, it means that where h goes to 0. In our formulation, it means that epsilon should go to 0. Epsilon, the tweak should be small. Okay, this epsilon. Then for calculating this, what do? It will become A2 minus A1 over epsilon. Am I right? Yes, I think that's correct. So this is numerical calculation. But for example, for this one, let's consider this element. What does it mean? Corresponds to C and F. So it means that I have E, F plus epsilon. It gives me some, sorry, eta 1 becomes this. Eta 1 then becomes A3, B3, C3, D3. Okay. So, and this is corresponding to C. Therefore, this value is what? Equals C3 minus C1 before change over epsilon. Right? I'm just using the definition of derivative, which I even didn't memorize. Okay? So this is numerical derivative. Did you get it? In this way, people are lazy in deep learning. They don't want to calculate the derivatives. They just do numerical derivative. Okay? So that's one thing. Let me continue with this, and then we will stop wherever we are over time. Okay, gradient vanishing and explosion in long-term dependency. So in recurrent neural networks, so as in deep neural networks, the final output is the composition of a large number of nonlinear transformations. Okay? This results in a problem of either vanishing gradients or exploding gradients. Do you agree? Because when we have too many in long-term dependencies, we have the window is very big. So I have too many multiplications of the gradients over time, through time. So if each of them is a bit smaller than 1, then by multiplication of all of them, we'll have vanishing gradients. If all of them is slightly above 1, we'll have explosion of gradients, right? By multiplication of them. Okay. Therefore, especially in long-term dependencies in sequence problem, this problem is explained in the following. Recall equation 2 for dynamical system. Do you remember this? Okay. By induction, the hidden state at time t or ht can be written as the previous t time steps. If the subscript t denotes the previous time t steps, we have by induction this. So what does it mean? For f theta ht capital T xt plus 1, then you feed it to the next one, to the next one, so you will have all of these. This is by induction, right? Then by chain rule in derivatives, the derivative of the derivative of loss at time t with respect to LT, what is it? Derivative of LT with respect to theta, the parameters are these. You can write it as derivative of LT with respect to HT times derivative of HT with respect to theta for t in the window, right? So by chain rule again by chain rule, you can write it as derivative of LT with respect to H capital T times derivative of H capital T with respect to HT times derivative of HT with respect to theta. Okay, why? Because of this. Because derivative of chain rule. Then according to equation 2 that we had, so derivative of HT with respect to theta, you can write it as derivative of FT, because I'm replacing HT with its formula. FT with HT minus 1 as input and XT. This is the definition of HT in the dynamical system, okay? So we have this. Now, we found this. We know that the derivative of H capital T with respect to HT, you can write it by chain rule as this. Derivative of H capital T with respect to H capital T minus 1. Derivative of H capital T minus 1 times, or with respect to H capital T minus 2, etc. and so on. For capturing long-term dependencies in the sequence, T should be large, right? The window should be large for long-term dependencies. This means that in equation 23 and equation 22, these two, the number of the terms becomes huge. We have a lot of multiplicated terms. On the one hand, if each derivative is slightly smaller than 1, we have gradient vanishing. If each derivative is slightly larger than 1, we have exploding gradients. So gradient vanishing and gradient explosion is common in recurrent neural networks, especially if you want to capture long-term dependencies, okay? Note that gradient vanishing is more common, okay? There exists various attempts for resolving this problem, and some of them we will cover, okay? And what I don't go over these, just we'll continue in the next session. But these methods are close to identity weight matrix. The other one is long delays. The other one is leaky units. The other one is echo state networks. And then also long short-term memory networks and GRU, gated recurrent units. So we'll cover them, and afterwards, I think attention mechanism and then other neural networks will cover. Okay, thank you very much.